Hello, everybody, and welcome to this stream by me, the one, the only, the perfect Darjan. So, what do we have for today? Well, I'm not going to surprise anybody. We're going to continue with what we were doing in the last stream, which is to complete the LZSS derivative compressor. So before we start, there is just one edit that I have done off stream, and that was regarding the main function about compressing a current chunk, in which the idea about sliding window compression is that you try to find a match of the current chunk, so the byte starting from now plus 1, now plus 2, etc. And you're trying to find a match in what we have in that famous sliding window, so something that we have compressed already. On stream, the condition to say that yes, we found a match was that the length of the match was over 0. And I have changed that to distance is over 0. So why is that? Basically because we're going to do some shenanigans with the length. Going to be honest with you, maybe not today, but I wasn't sleeping last night because of the heat. I figured it out a way I want to optimize this find match function. Again, not today. We're going to basically write the code by the book. But I thought that it could be pretty cool if we could do some less than honest things with the length. However, for the distance, it's actually very simple. Distances are always valid, starting from 1, like 1 in the path. It can never be 0 because 0 means you want to match with yourself. That is never going to work. So this simple test works 100% of the time. I don't think it has many side effects. So that being said, let's go and build our find match, because last day, once we arrived to this point, we went into a side quest to increase or to enhance the API of the encode trait to give us 4 numbers that are going to be useful right here, right now in find match. Let's see why. So first of all, we need the goal, right? This is what we want to match as much as possible. That's our goal. And our goal is a buffer from now. So in theory, the buffer could just be from now. However, that means that we can have a match as long as it can. But we know from this enhanced API that if we have a reference, we have a maximum length associated to it. Okay? It cannot go beyond that. So in fact, the buffer needs to be shrinked either to its natural length, or if that maximum reference length is shorter to that, so basically the minimum between the self buffer length or now plus self encoder get max distance, no, length reference. There is. All right, so that's our goal. Yes, of course. And now it doesn't exist by itself. There we have it. So that's our goal, right? And that doesn't need to change because that's what we want to match. Match with what? We need to find matches from the window. The window is positions in the buffer in the past, right? So given a distance starting by 1 in the past, no 0, until the maximum distance that is possible to encode. And once again, we know that, right? That is self encoder. So that's thanks to the work that we did last stream. So that would be get max distance reference, right? So between this and this, those, the buffer starting by now minus distance, it should be enough. Now, we are going to match also a slice. And so we also need to calculate the end of that slice. For the moment, we're not going to do that because we have already restrained the length here. So I don't think we need to do the work again with the potential match, right? The instantaneous window is self buffer starting by self now minus distance. So the problem with this is initial condition. Okay, this is very important. At the start, when we start compressing, now is 0. 0 minus 1 is minus 1. This is going to crash from the beginning. All right. So we need to have a quick exit. What is the quick exit? There are 2 exits, actually. The first is when now is 0. Okay, because if now is 0, we are not going to find a valid match. And remember, not finding a valid match means returning a distance of 0. The important one is this one, distance. Let me show you again. The second element, the distance, when it is 0. But there is another condition. And this happens typically at the end. And that is when the length of the buffer is actually smaller, not that the maximum length of the reference, but the minimum, what we call the break-even length. right? So the self buffer length is smaller than self encoder length. But length, that is not going to work either, right? We're not going to find a match. It is actually impossible to find a match. So once we have set up those edge conditions, now obviously this is always valid because now it has to be more than 0. Once again, I don't think we need to restrict the slide here because we already are restricting the length in Go. But that means that we need to be careful in the function that we're going to make to compare the instantaneous window with Go, that Go length is the one taken into consideration. And we're going to have a best of variables, which are the best distance and best length. Okay, and let's keep it like that. So now we're going to find the match length between Go and instantaneous window. Okay, this is a function that we need to do, compare prefix. That is going to provide in the output what is the length of the match, which can be 0 if directly the first byte didn't match at all, or it can be any number. So then what we need to do, obviously, if that match length is larger than the best we have so far, then we change it, right? The best length is our match length, and the best distance is this distance. But here's the thing. There is already a basic optimization. So what's happening now? It is right. What, more or less? No, I don't think so. Maybe this, I think this is this is forcing this. Anyway, let's continue. What I was saying is there's actually a clear optimization here, because we only update the best match when it is over, not when it is equal. If the match length is the maximum possible, then we're already good to go, right? The maximum length is this one. So basically what we're going to do is we're going to capture the value in a variable. I know this Rust compiler is very good, it's going to make very clever tricks, but just in case, its length is equal to this. and then max length is equal to this. And now here we can do that optimization. If match length is already equal to the maximum length, we directly return that length, which is the max length. The reason why I use max length and not match length is I'm betting on the compiler to optimize map length already. I mean, compiler, if it's very smart, it also knows that match length is equal, so whatever, but just in case. Max length, and now the distance is distance. And if that's not the case, then we optimize this. So at the end, you just need to return max length, best length and best distance, right? That's the idea. But what if that best length is not at least the break-even? Remember that that is a precondition that we have assumed here, is that if distance is more than 0, then the length is above the break-even. Right? And break-even is the minimum. So basically what we're going to do is we are going to get also the minimum length, which is break-even. And now, and this was the trick that I was thinking the other day, we are going already to have a base distance, not of 0, but of min length minus 1. Sorry, the other way. We're going to assume an already best length of minimum length minus 1 on distance 0, meaning if we fail to find a match that is above the initial best length, which is min length minus 1, meaning if we don't find a match length that is at least min length, so the break even, then we don't override best distance. And because the default for best distance is 0, that will mean that we will return here as distance of 0. Okay, so basically returns whatever distance 0 if no match at least gets break even length size was found. Now guarantee thanks to this trick. Okay, so I think those are two nifty implementations to the algorithm. So now let's go for compare prefix. And this is very simple, right? Actually, there are two ways to write it. This method can be written indexes or iterators, and there are good implementations of finding a prefix using an iterator. But I'm going to be very honest, I did very limited tests yesterday, and everybody was saying that the iterator solution was faster. And in, again, very limited tests that I did, the iterator solution was actually slower. So I don't know what is happening. So I'm going to implement it with an index, and later we can do a proper test when we do proper compression and try to write this method with iterators and see the impact. All right, so let's start with that. So that's a simple for ex in 0 until, again, remember that we don't need to restrict the length of the window because we're already restricting the length of the goal. We don't need to return here because it's the end. Okay, so what's happening here? Oh, forgot to this. All right, so basically this writes all the code. But obviously, because there are two things that are missing. First, no, not first, because we're gonna have what we need is an application that uses the API of the compressor. Yes, I was right. We're missing one thing. This just compresses one chunk, so only one position. The actual method what does it do? So basically, there are three types of compressors for this kind of compressions. The first one is a pin window. Let me see if I can. Okay. And let's see if I can make this work. Never try. So when we are compressing, basically the complete buffer can be divided into three sections. Where do I have a test? I just want to add a test. How is it to do? Insert textbook. So what? Okay, here. So the important part is now, right? Now divides the window right? The window can start from whichever place. And can I change the line? Tutti tutti tu. How can I change the formula? The lines. That's a line color. I don't want to change the line color. I want to change okay. Let's add a dimensional line. All right, so here we have the window. And from here to here, let me note this down. We have the check. Okay, this is the chunk or the goal. Right? And it starts with now. The important points here is that this distance is defined by the max reference length, while this one is determined by the maximum reference distance. Right? That's actually why we need those two parameters, right? As you have seen in the find match, etc., the goal is now the slice that starts in now until now plus max reference length, or the end of the slice if if the slice is shorter. You need to take that in consideration. And for the window, we don't start from 0. We start from now minus max reference. Sorry, we're not taking that into consideration. Oh, yes, here. But here, we're making a mistake. Because what if we are in a scenario like this? And now minus max reference distance is a negative number, right? So that's a good thing that they made a diagram. So now this has to be the minimum value to now and self-encoder. Now, one crazy thing about this is that when now is equals to 0, this would work. Because it would try to do an iterator starting from 1 to 0. That doesn't work. It directly goes out and brings us a distance of 0. Right, so we need to check for check test for equals 0 because of the is written. Right? Maybe. But for the moment, we're going to make a test like this. Anyways, there are actually 3 parts of the buffer. And you may ask, okay, I can see 2. Yes, but the third is this remaining here and this remaining here. And remember that I said that there are 3 types of compressors. There is a first type of compressor that we can call it actually a penguin. Okay. Here, the trick is that we absolutely know that the buffer size is going to be less or equal than max reference distance, right? So in that case, we never need to move the start position. We don't need to calculate this in the for because it is always going to be safe now. Okay, because the max distance buffering is so large compared to the size of the buffer, and now it's part of the buffer, so it makes sense. So this leads to an optimization. File match can always go to max distance. The second type of compressors is linear sliding window compressor. And you may say, we don't have that. So, okay, let's keep it like that at the moment. So let's move on to the third type, which is when we are doing how it is called, the queue, sorry, the word just disappear from my mind. Do I know? So I know that one implementation is about the queue, which is not the one that I want. Ring buffer. That's it. Ring buffer is sliding window compressor, and that actually looks like what we have here, right? We consider that this part here is things that we have already compressed, but they are too far away from now that they cannot be used for the window. So that basically, this is now free space. And this too is free space, right? Because we don't have anything that can be compressed because it's beyond our current goal of compression. So in our ring buffer sliding window compressor, what happens is as we compress a chunk and we move now, reminder, when we compress a chunk, we move the now pointer. This part of the red ahead, and by the way, this part of the, what? Sorry, I have just explained myself. This part that is unused and this part that is unused become the red ahead buffer. As we move now to the right, we need to read from the input and put data here. So the channel is always of the maximum length, obviously until the end of file, right? So that is going to be one of our last goals in this series, meaning work with a buffer that can work as a ring buffer. That way we avoid doing copy from buffer to buffer, but directly read from the file into this part or this part. And yes, we need to deal with a little bit of shenanigans because of the fact that this part, and even the window or the channel can be over the modular limit of the ring buffer. That's why I want to keep this as one of the last goals, milestones, if you wish, if you will, sorry. But what about this one? So let me quickly do okay, this. Let me do a quick detour, maybe not so quick. I'm going to try to make it as quick as possible to the Kafka protocol. And this is just an example, it's just a protocol that I know about. So the Kafka protocol, okay, it's from the Apache Kafka project. So the Apache project is basically a project to have a message broker and have applications sending data to those brokers and then other applications reading messages from those brokers, right? So there are three elements in place, which are what are called the producer, and then the brokers, which are the cluster, and then we have the consumers, right? And the producer, the brokers, and the consumers are in different places in the network. So basically, when the producer is sending data to the broker or the consumer asks the broker for new messages and the broker sends messages to the consumer, here we have network, and here we also have the network. So Kafka doesn't use an HTTP based protocol. It is a binary protocol, but in short, we're going to call it the Kafka protocol. Producer side, when your application or when you as a developer wants to send a record, you send the record to the producer API. Okay, the producer API does several things. The first thing that it does is to serialize the record. This allows the Kafka protocol to be generic. You can send whatever it wants for as long as then you configure a serializer that can do that, like JSON, Bravo, above, to name a few. Right? And after serialization, other things that happens, but at the end of the day, the message is put into an internal queue. So, okay, so someone is watching this and they know about Kafka, they know that I missed this. I'm going to put this. Yes, I know that I missed this. So the message is put into internal queue, and then one or more attention to send you to, right? But that's the basic between producer and the broker. But here's the thing. The protocol allows for optional compression of the record, of the serialized record, as it is put into the internal queue. And this compression is, in my opinion, quite useful, because that means that the record is compressed from here to here, is compressed inside the cluster when the record needs to be sent from one broker to another for replication or whatever. And then when it is sent from the brokers to the consumer or consumers, plural, that on that record. So every single byte that we can hear saves multiple bytes in network bandwidth end to end. Moreover, when the producer compresses the data, it keeps in a header which algorithm was used. So the consumer, it doesn't need to be configured. It's going to read that header. It understands which compression algorithm was used, and it compresses on the fly, completely transparent to the user. So quite useful. But here's the thing. What are we compressing here? Let's say that we want to make something like this. What are we compressing here? We're compressing a memory slice that is completely known in size and content, because it is the output of the serialization. And that means that we already have that as a buffer, right? We're not going to add anything afterward. That's not a thing. Moreover, if we do things like batching here in the internal queue, mean that we add multiple compressed records into the same internal queue, the output is still going to be linear, and at least in the Kafka protocol, there is a maximum limit anyway. So we don't need a ring buffer. Okay, so a linear sliding window compressor is when the maximum buffer size is known, but it is larger than the max reference instance. Okay, and this is useful for example protocols similar to Craft. So it's not the buffers, it's input. So what happens is that we end up with three very similar implementations of the compression algorithm when we have something like this. Let me, by the way, save this. No. So now let's come back to the project. So how do we implement a pinned window? As I said before, a pinned window is just that this number is always going to be less than this number. So we don't need to calculate the minimum or the maximum reference distance. It is always a known thing that the loop is going to loop from 1 to self now. Okay. So in case, so that is an optimization, true, but it's a very slight one, right? It's basically by match, which is a lot, don't get me wrong, but by match, you are just removing this calculation, which is kind of quick, don't get me wrong. The problem is that it may be difficult for the compiler to know that this doesn't change because it's a function behind that trait. So it cannot guarantee that this doesn't change from call to call. But anyway, this is very fast to implement. And then a minimum, which again, is very fast to implement. So not ideal for a pin window compression. And we can think in the future to have a variant for that. I don't want to do it now because maybe here we can do some optimizations that the pin window compression can still take advantage of. So I'm going to keep it like that. And this is the implementation for linear sliding window compression, which we know that for everything, for the window, from the chunk, and for the red ahead, we have a linear buffer, so we don't have split buffers around the ring. And then we will write later in the future a version of this that can deal with ring buffers. All in all, right now we're writing a linear sliding window compressor, and that means that this compressor is just moving from the beginning until what? Until we reach a moment in which the size of the chunk of the goal is smaller than the maximum length. In that case, we may want to stop. Why? Because if we assume now the second case a linear sliding window, as we move now and we arrive this and now this, when we arrive to this place, we can say, hey, hold on, I'm going to stop compressing at the moment, just in case the user wants to extend the buffer to continue compress, to compress. And if that's not the case, Then we add to the API a flush. Flush being basically compress everything that you have until you reach the end. This is basically what we did in my Illustera, in what we did before I could keep the VODs in YouTube. So again, compress, it has some limits. What is the limit? Is that we're going to compress while surplus not plus self-encoder max reference is less or equal to the self buffer length. Okay, while we still have plenty of things to compress, then we can compress. How we're going to compress? We're going to compress the next chunk. And how to implement Flash? We compress until the end. And now we have a proper compressor that can compress a full buffer. Now, the only thing is this, that I'm keeping pub as public. In reality, it should be pub. No, it has to be pub because of the tests, right? If you want, the tests are in the crate are a different module. So we still need to document this, but we can start doing some tests. And we're going to make tests with compressed current chunk, because I think the test cannot do tests on private functions. They can. They can. Let's try. So we're going to first create an encoder. And that means that we need to create an encoder. Okay, and the encoder needs a parameter about EOF. We're going to set it to true for the moment. And then an encoder config with a break-even length 3, max length reference 1.27, max distance reference of 127, max length literal of 127.2. All right. See the stupid thing, right? Yes. There. So with that, we have an encoder. And now we are going to create a compressor. And the compressor is created with just a mutable reference to the encoder. Okay. So now yeah, you see there is a problem. Is that the buffer is internal? We don't have access to it. That's because we are missing a very important method. Okay. So now No, there is a problem here. Here, there's a mistake somewhere. And close the limiter. I see. All right, well, perfect. All right, so the stream is already over 1 hour. So as it is usual, we're going to take a break now. I want to make some text with some redeemables. All right, so redeemables are still not correctly implemented. I mean, I can see it in the chat as you see the pop-up. Well, what can we do? Things to improve. There's always something to improve. So I'm going to start some music. And yeah, I will see you in 2 minutes. Stretch, especially if you're like me, already getting like a shrimp. Hydrate if you are suffering also from severe summer weather. Even if you don't, maybe you will also uh, profit from drinking some water. And I will see you in a couple of minutes. And we're back. So let's continue. So we're testing. And the first thing that I want to compare is just the compare function. Sorry, the first thing that I want to test is the compare function. We just got our buffer. And now let's take a look at the function. One thing that I found, I was thinking, is that this function is actually not a method, right? If I remove this, the function just works. The only problem, and that's the error, was this one. All right, so compare just compares two strings. It doesn't matter where they come from. So actually, we don't need to create any compressor encoder or anything at all to test compare. The only thing that we need to do is to create slices for code. And let's say that our goal is one, two, 1, 3, right? And we want to assert that compressor compare prefix in the goal and of 1, 2. So one important thing is that this function assumes that the window is longer than, so the length of the window is longer than the goal. Is that true? Yes, it has to be true. It has to be true. So we need to create something that is as data as long as this one. And so let's start with 0, 0, 0, 0. So 1, 2, 3, 4, 5. Let's keep it with 4 at the beginning. So we need to assert that this is going to return 0. Okay, test compare works. And let's continue. One, two, 3, 4. No, sorry, not 2. 3. Let's have a couple of tests. And this is longer. It still finishes with a 4. And when we have a difference, no, we don't need another test. All right. So compare prefix. That's what it says in the thing. Finds the length of the longest prefix on goal and window. So that function is tested. Find match. Now for this one, this needs the proper encoder. And that means that we are going to need this chunk of code. And of course, we're going to need the uses. There. So find match. First thing that we need to test is at the beginning. Self now equals 0, which is the start. Right at the start, self now is equal to 0. So no matter what, a find match by itself is going to fail all the time because we don't have any function, not even a private function that can change the now pointer. And I don't think we have. I can try to see if we have the ability to manipulate the now from here, given that we're inside the module. But at the beginning, it is correct that find match is going to return a 0, 0. No matter what. Go to a macro. Yeah. It doesn't need me to go in. Find match returns a 0, 0. Perfect. So that's the first condition. The second condition is when the buffer length is less than the minimum length. So at the moment, yes, the buffer is empty. But the problem is, can we change? No, I can't. Yes, we can. Perfect. So this is edge case. No, This is in each case when the chunk is 6, 1, no. Okay, these are the two cases here. Now let's continue. Now we're defining the goal. We're defining best distance. And then we're going to do the loop. So now we need to find something that can fail a match or pass a match. So to fail a match, so first of all, we need something as a window. Okay, let's say that we're going to have in the window a single byte, which is a 1. And because now is equals to 1, the next byte is actually now. This is the starting of the goal. So for as long as this is smaller than, sorry, it's different than this, find match is also going to return a 0. Now, important, we don't want to fail because the chunk isn't long enough. Okay, we need to make sure that we are not exiting from here. So the length of the buffer, this is wrong. That's a good thing that we do test because this is wrong. We need to exit when this is less than now plus minimum length. Yeah, so now is equal to 1, mean length, which is the break-even length, is 3. So if the buffer is less than 4, we cannot find a match that is long enough, which makes sense because we will then find a match starting from 1 of size 3, which is the minimum 1. So we need 4 bytes. 1, 2. All right. So this doesn't need to be immutable. I'm extending it. That makes it by definition need to be. Oh, yeah. Sorry. And now we are going to assert again that we're not going to find a match. In this case, what should happen is self now is equal to 1, buffer length is equal to 4, which is equal to 1 plus 3, so it's not less than, so it should continue. The goal is between buffer length, which is 4, and whatever. So this is going to be minimum. It's going to be between now and 4. It has the length of 3, best distance of 0, best length of mean length minus 1. So now this assert is actually wrong. Yes, correct. That's a good thing that we did that, because now we know that we're actually exiting from the correct place. We are exiting because the for loop didn't find a match. So we are returning best length, which is minimum length minus 1. Remember, minimum length is actually the break even, which we have configured in this test to be 3. 3 minus 1, 2. So it should return a 2 with a best distance of 0, which is what it says here. It's absolutely correct. So this actually is equal to E get the given length minus 1. A, no, C. No, I see. Oh yeah. Oh yeah, oh yeah, oh yeah, oh yeah, oh yeah. Because we have this mutable model here, and then we cannot use it here. Okay, well, let's do it by here. All right, and test find match still works. And finally, and now we're going to get buffer of 1 equal to 1. So let's try this again. Match. So let's get the buffer again and just change the first. This test should have failed. No, this should not work. Sorry, buffer. I don't see what's happening here. Do something else. So now if I move now to here, that is a match of 1, 2, 3, 4, 5. But it still says there is no match. All right, not yet implemented. So to do, so the for is getting inside the to do. So the problem with this test is that they only work if you do real debugging with a real IDE. I'm just using a test editor. Oh, forgot how to run an example. Anyway, perfect. Entire compression. Units import. Okay, perfect. All right, so instead of a test, for the moment, we're going to make it as an example, because then we have input and output. Yeah, but we lose access to find match. And we lose access to now. That's not a problem because we're just debugging. So we're just going to make this public and this public. One, two, one, two, one. To zero. So let's see now. Find match. Dun, 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 dun. And go. Is 1 to 1. This is the goal. And that's correct. And now when we are calculating, compare the instantaneous window. Distance. And instantaneous window. All right, so now we know the problem. Yes. So that was the problem. I guess you don't know what happened. When the window was too small or when there wasn't any match, there wasn't any problem. The brain sat down. Now, the distances that we need to take into consideration are basically between 1, which is now -1, until the beginning of the buffer. And the beginning of the buffer is self now in this scenario. And that has to be included. And I forgot about that. Okay, basically, this would be the same as having a for between now and not including self now, and then reverse the direction. That was it. Now we have a match of length 3 at distance 2. Now is 0, distance 2 is from the beginning. Correct. So starting from here, we have a length, a match. Here, distance 2, 1, and 2. A length 3, 1, 2, 1. Perfect. Let's remove impedance here. And now let's go back to the tests. And now this phase and section. Oh, now we have actually a very long match. Let's try now. So with 1, we have a match. Basic match, second match. So we have one with size 3, but that is actually because that is the end of the slice. I want to make the same result, but actually having something after that. So I'm going to push, let's say, a 3. And this should be exactly the same. Perfect. And because of the print lens that we made for the examples, we know that it has actually tried to find a match here, which is correct. So maybe we don't need the test for now 0 because of how the loop is written. It was written Here, minimum save now. Let's try that. So let's remove this. Yeah, and it works without crashing. So I think that this works. And it works. I know that I don't need this to be public, and it is reachable by the tests. And we could do some tests and some documentation here, but I'm not going to lie to you, or I am getting a bit sleepy because it's still too hot here. So I want to do something that is that is more exciting. So this should compress. So I'm going to call this a commit. I'm going to commit this change. I mean, 194 lines, and it mainly works. Linear slide window fit. Okay. So sign off and commit. Perfect. So what's next? Next, what I'm thinking is actually writing. I don't know why I closed it. I think we should write a basic compressor. For that, I'm going to take a look at what I did before. So first of all, I'm going to get a handle. And sorry. And Like to do like this. To create our compressor. And then we're going to get standard input. And we're going to return in the buffer. So now we have a full file in the buffer. So now if we call compress in Flash, we should compress everything. I'm seeing that the bit rate appears unstable from Twitch. Everything looks fine on my end. CPU utilization 1.2%. And I have a good throughput, I think. Drop frame 0. The bitrate matches with what Twitch says, but Twitch says unstable. I don't know. Maybe there is something playing in the World Cup and everybody's watching the match. Anyways, I think it has the stream has already shown briefly the disconnected image. So we're going to run with this. And what do I mean by that? So now the thing is that our encoder, because this is a mock encoder, this mock encoder has a writer that contains the output symbols. The problem here is that because we pass the encoder as a mutable reference, we cannot use it. We cannot use this one. Let me show you. If I try to get the result, oh, it's actually working. I didn't think that that was the case. Well, cool. What? Ah, it's single. Cool. We have a failure. So it panicked in at leaper S line 75. Slash pending literally. That's good, because that means that we have called so flash pending. So we are accumulating literal. If is sum and it is short, return okay. If not, then if it is sum and the length is obviously the maximum, we call flash pending literal. So self pending literal must be sum. And the other place we call it is here. Yeah, and here we call it unconditionally. That's a problem. And that's why this was a debug assert. Because now in when we're going to release mode, the test is done here as it should. We don't need to double check here. Brilliant. Now, the only thing that is wrong is that Flash is not sending end of file symbols, even if we have configured encoder to have end of file. So how do we proceed with that? Once again, it is not this compressor, it is the user. We should decide if they want to send end of file symbols or not. But the thing is, here the user, me, and I have decided to send them. But I have no way to tell the compressor to do that. Okay, there is no entry. Because Flash doesn't do that. So now we have a problem, is that if we write end of file, this is unconditional. Right end of AOF should fail if call from an encoder that doesn't need end of file. But here's the thing, is how does it know? It cannot know it, right? Because it gets the configuration, but it doesn't get the fact that it needs an end of file. On the other hand, we cannot promote needs EOF to be a parameter, an argument for new of the compressor, because it could be encoders that never use end of file, and because there can be many encoders, and the new method is not part of the encoder tree. So that means that we need a function that returns the configuration of EOF with an possible symbol. And now in the encoder, we need to implement it. So finally here in the compressor, when we're calling flush, and we can actually say, okay, if it needs end of file, let's set encoder write EOF. If not, in conditional okay. And that means that when I run this, here we have the end of file at the end. If I change the configuration, we don't have the end of file. Perfect. So now we have the flash, and we have the list of symbols. Are they correct or not? Match symbol. If it's an EOF, if it is as, oh, we are not exporting symbol. If it's a symbol literal, and symbol literal has a vector, right? Yes, a vector. We're going to print literal with the vector to CTF TF chunks now. TF, so TF, it always drives me crazy because we did it for the other compressor. Okay. Or manner. Oh, yes, missing an arm because for the other arms, you're just going to print this in. So let me check. Yeah, it's not an it's an unwrapper. And we have the match. Oh, let's take a look. We're not going to see everything, but we can really see the literals. So it started with a literal hasta educat, a reference with 3, which is ION from compression, to educational code regarding class CLA SS, so no, SIC, no, CLA SSI. Yes, in compression, that's correct. Class C, and then AL space from educational, data, the full compression word from here, algorithms, hasta, up to, yes, this, and then script, and then shown from educational, and then we have longer than descriptions of reference. It may interesting. Space CO. Yes, I can call here. Contain background information. So I'm not going to go over the full file, but I would say that yes, we did it. We have the compressor up and running, working. I mean, the compressor compressing only to the mock compressor. But that is good, because that means that the next step would be to create a real encoder that can encode to file. That's one thing. What else? Yeah, I think we're going to make a commit with the little changes, which are let me see. Yes, the bug that we had with pending literal, and then the additions for great end of file, and then for the encoder, mock coder, the implementation we need OF. So now the problem is that now we have something that I don't like, is having commit doing two things, in which one of them is a fix, because we are fixing the part in which we are accumulating compressed current chunk. this anyways, let's do it anyway. Track compressors. But anyways, so stage commit fits compressor how is the class called actually? Compressor, yes. Fix compressor compress current chunk cause it has to be in order. Call flash binding literal conditionally. Chunk fix compressor to the time. This fixes time to call coaching. It's also let's it's F to the code trade, so it can image G but use but G compressor slash. Sign off. Now we add another commit with a compress. This is a feature. Compress and samples compress. And I think the last commit that we should do at this step would be, as we typically do at the end of one of the efforts, is to move this into its own module. So let's do that. Buffer LZSS like compressor. right? So now this should work. Oh, except that now encoder. Gotcha. So this works. And the one that doesn't work is example. So we have that, we have the capability. Oh, cool. So in mock coder, yeah, you have this line. We're going to keep it. No, in line 67. That's right. It's not to this. Hmm? Yeah. So we're going to, yeah, it's just a single line. So we have repeat test examples. For documentation, we're missing a lot of documentation. I don't think I'm going to do that I'll do the downstream and add the documentation for the compressor class. So with all that said, um, what type of, how do we name the commit? De facto. Compressor to its module. This also includes some EP fixes. And there we have it. So now we have a compressor that compresses to the mock encoder. And the next step would be to create another encoder that can actually encode to file. So I think that merits its own card. So off screen, I'm going to do a pull request about when I'm going to complete documentation. I will see if there is another test that can be added. Then with documentation and tests added to with more commits, I will create a pull request, merge, and then create a new card. But I'm going to create a new card now, because I can do that. So I will create a new issue, which is to implement a by oriented encoder. So why is that? Because one of the things that we're going to do is we're going to change the encoder a lot. If you were here the other day when we took a look at the LZSS